Boa tarde a todos. Sejam todos muito bem-vindos ao nosso segundo workshop de Cloud e computação de alto desempenho. Nós teremos duas palestras de professores convidados, uma agora, que vai começar já já, e a outra amanhã, meio-dia. Nós teremos também duas sessões de apresentação de trabalhos, uma hoje às 2h30 da tarde e a outra amanhã às 2h. Todos que já foram inscritos no workshop já receberam por e-mail o link das salas do Meet para entrar nessas sessões de trabalhos, e a gente pede, por favor, que vocês entrem com os e-mails que vocês se inscreveram, tá bom? And now I'll switch to English to welcome and introduce our first speaker, and he's Claude Tadonki, and he's currently a senior researcher and lecturer at ParisTech Institute in Paris, France. He holds a PhD and an habilitation degree in computer science from University of Reims and from Paris-Sud University, respectively. After 6 years of cutting-edge research in operational research and theoretical computer science at the University of Geneva, Switzerland, he relocated to France to work for EMBL, University of Paris-Sud, LAL-CNRS, and then ParisTech. His main research topics included high-performance computing, combinatorial algorithms, and operational research. Claude Tadonki has worked with several laboratories and universities, has initiated various scientific projects and national and international collaborations. He also has given a significant number of computer science courses in different contexts, including industries. He acts as a reviewer for high-impact international journals and major conferences, and he has also published numerous papers in journals and conferences. He has actively participated and co-organized a number of international HPC conferences. So welcome, Claude, and you can start whenever you want. Thank you.
Ok, muito obrigado, Rafaela, por essa apresentação. Muito obrigado para a Lúcia pelo convite pelo esse workshop, convite pelo todo o que fazemos junto, convite para ser aqui no Rio com vocês. Me chamo Claude Tadonki, sou da ParisTech e vou fazer esta apresentação hoje aqui em inglês. E é um prazer para mim, um honor sempre de fazer coisas com a Academia do Brasil, porque é uma cooperação que é muito importante para mim, para a França também. E isso faz parte dessa colaboração. E estou muito feliz e lisonjeado de fazer esta cooperação com vocês. Então, vou dar esta palestra em inglês, porque é uma palestra técnica, né? Well, now I'll switch to the talk itself. Today I'm going to talk about efficient management of data in a geo-distributed cloud. This is a joint work with my student who is doing a PhD with me on especially on this area of the cloud computing, managing big data application on the cloud in general, and specifically on a geo-distributed cloud where you have several data centers that are located in different places. And Mustafa, the name of this PhD is Leila Bush, and Mustafa's back is a co-advisor with me. So it's a colleague, he's a colleague, a good colleague and friend of mine. Okay, so what is a geo-distributed cloud? In general, you have several data centers that are located in different and distant geographical locations, as you can see in the figure. Typically, this is, you can see this in federated cloud. So you consider a different cloud and then you just federated them using the network. But it can be a unique cloud which use different data center in different locations. You can also have this if you try to connect different supercomputer that are located in different places in the world. And this is common in HPC when we want to run a very challenging workload application. So for us, the model is nearly the same, either the cloud or connected supercomputer in HPC. The standard way to get a large cloud is this connection. So typically, if you are going to a cloud, which for you is not sufficient in terms of capacity, in terms of processing, then you might need to consider a federated cloud, and then you will get this kind of configuration. This is very good for different kind of application. The first one is the class of application that has dynamic content and on demand, like social media streaming. With social media, the problem is the content is changing because you have new entries that are provided by the user, and the demand is dynamic because what people are asking to get from those servers is not the same, and it's not the same from one region to another. So for instance, if you have a server here in Brazil that stores music from Brazilians and people are in France and they ask for it, then the data center here in Brazil that house those records will move the record to the server in France and people will get it. And it can be the contrary. So you have the content that is updated dynamically and the demand is also dynamic. So in that case, you have in general a federated cloud like this, and data are moving from one data center to another. This is very interesting also when you have an application with heavy storage and bandwidth requirement, because if the storage is very heavy, so you need a very larger space to store your data, then you might consider several data centers that way. I mentioned the case of HPC application. For instance, if you consider genomics application, you might have the configuration where the data are not necessarily in the cloud that you are using, where you have your application, for several reasons. So you might have, for instance, the genomic data of the Brazilian ecosystem in a server in Brazil, the same in the US, the same in France. So the storage here, it might be heavy, and you will require several data centers for that. I mentioned the genomic, and this is the last point is very heavy costly calculation. This is HPC, as I mentioned, Federation of Supercomputer. The connection between those data centers that you can see in the figure are direct in general because it's wireless, or it can be indirect also, because even if we might think that just because the connection is wireless, then there is no way to imagine that there will be no connection between two data centers. In theory, that's true. But in practice, for instance, some restriction, political restriction, might lead us to the fact that between two data centers, there is no way to send the data directly. In that case, you will have to consider routing algorithm. But here in this work, we don't consider this case. We just assume that we have a complete graph. So we will want to consider a routing algorithm to bring the data from one data center to another. We will assume that the graph is complete. So between two data centers, we have a connection. So the question will be the bandwidth, and then we will try to minimize the overall data movement during the execution of a given HPC workload. So the model that we have here represents a single cloud system. Even if it's federated, we will finally see it as a single cloud with different data centers that are spread over different locations. So from the data viewpoint, the data are organized into data sets. So we manipulate, we model here our data considering the level, the granularity of a data set. It can be files, okay, typically. A data set are exchanged between the data center, as I said, through the network. So there's explicit transfer from one data center to another. And the aim of our work will be to manage the cost of such transfer. For large data set or lot of requests, the cost of moving the data in that condition might be prohibitive. So if your data set is too big, just sending it will be costly. If the task is located elsewhere and is repetitively asking for different data set, then you will also have a lot of data transfer. This reminds me technically the situation that we have in parallel distributed computing, or even in shared memory computing with what is called NUMA architecture. Because in NUMA architecture, even if the memory is accessed by all the core, what is called shared memory, but in practice, those memory are partitioned. So if the task that is running is in one partition and is always requesting the data that is in another partition, then you will have a lot of transfer from the network, and for the NUMA is the QPI link. And this also always incur a severe overhead on top of the execution time of your application. And this is the main reason of weak scaling when we are in a parallel context. And here, this overhead will be the overhead of exchanging the data between the data center. Okay. So a pure static organization, which is sometimes what the provider offered to you, might not be suitable depending on the application. So that's why the aim of our work is to build a strategy that we will give to the provider to indicate to him how to organize your data, where to put each data center, and later on, where to create copies. I will explain it later. So the storage capacity is likely to be rich if there is no specific attention paid on data management. This is another problem. So not only the problem of the prohibitive cost of moving the data, but if you just put the data without any specific plan, then maybe you will just saturate one data center, and then the other will remain free. So you have two problems here: the cost of moving the data, and also the risk of reaching the space that you have on a given data center. So the question here for us on this work is how to store the data set that we have for a given task. And later on, when the task is running, how to replicate the data set. This means that when a task requires a data set, then the data set is moved from its source to the data center where the task is running. You receive the data set, you use it for the task, and then you have to decide if you keep it as a copy for later usage, your own usage, or the usage of a neighbor, or not. So this will be the second part of our work. The first part will be answering the question, how to store the data set. So for each data set, where should we store it? So the hypothesis here of our work is that we don't consider task migration. So if a task starts in a given data center, it will just continue there. So there is no preemption. As I said, we consider a complete graph. So there is no routing mechanism. So between two data centers, there is always a link, even virtual. We assume, and this is important in the cloud, because we know that one thing that is specific to cloud is virtualization. So what you see at the virtual level is not what it is at the physical level. So here in this work, we assume that we are working below the virtualization. So this is typically, I say it again, something that will be run by the provider from our instruction. So let's give the input that we need here in this work. The first one is the task allocation. So in this work, we assume that we have a scheduling. So for each task, for instance, here in this example, we have 8 tasks. For each of them, we have an indication of where the task will be executed. So this is just a table, like you can see in this example. So we need it as an input of our work. The second input is the dataset requirement. For each task, we indicate the dataset that it will use. So now we have 2 inputs. And the output from our algorithm will be for each dataset where it has to be stored. So this is an example here of the configuration that's given in the table here. And this is an example of the results that our algorithm can provide. So you see that here we have 5 data centers, we have 8 tasks, and we have here in the figure the location of where the task will be executed. And in red color, we have the location of the data center that is indicated at the end of our algorithm. I repeat here that the aim is to reduce, to minimize the cost of data transfer among the geo-distributed cloud here. So this is the main purpose. We don't even care for this work about the running time of the task itself, okay? Because we assume it's already optimal. Okay. So let's start with static scheduling. So this is just a set of notation. This is typical when you want to model a problem. So you provide the set of all variables that are going to consider. Some of them are input, some of them are output, and the other are internal working variables. So an example here is the vector C, which is the vector of the storage capacity of the data centers. So we need it because the storage capacity is a constant. We cannot exceed it. The vector R, for instance, here is the vector of the read speed. Because when the data are on a given data center, we have to consider the read speed of that data. Vector W is the write speed, so read-write. And the matrix B is the matrix of the bandwidth of the connection between the data center, the bandwidth of the connection of the graph that we have, okay? This is some example. Then I will try to explain the main important variable that we are going to use. So at the end here, you see that we have 2 outputs. The first one is the vector phi, which gives for each data center where it will be located. The second vector S, it will be in the second step of our algorithm. It will just indicate where to get a given data center because of the replication. For a given data center, you will have, for a given data set, sorry, you will have several locations. So vector S tells you where is the best location to get that data set. Okay. Okay. So let's explain the main part of our model. The first one is the data center graph. As I told you, we are considering a complete graph. So the node of the graph are the data centers. And then you have a W, which gives you the write speed, R, which gives you the read speed, and B, which gives you the bandwidth of the connection. That's all what we need. Here, the vector psi is just to indicate really what we need, because the bandwidth is something, but we are interested in the cost of transferring the data from one data center to another. But that cost for a volume V is given by, normally it's given by V divided by the bandwidth. This is a classical formula. So if you want to transfer a data set of volume V between data center I to data center J, then the time will be V divided by B sub ij. But if I equal to J, then you are within the same data center. The cost should be 0. So there is no way to get 0 by dividing a number by another. So that's why, since we are V divided by B sub ij, we assume it's V multiplied by 1 over B sub ij. So this value 1 over B sub ij is another matrix that we create, and then we arrange it to correspond to specific situation. So that's why Cij is defined like this. When I equal to J, this means that we are within the same data center, then the cost is 0. When there is no link, but this is the more general case if the graph is not complete. When there's no link between data center I and data center J, then the cost is infinite. And otherwise, we just consider the 1 over B sub ij. So with this matrix, then the cost of transferring the data from data center or volume V from data center I to data center J is just V multiplied by Cij. Okay. Then we have the task. We have n tasks that we call T1, T2, and Tn. And for each task, we have the vector alpha here, which is, as I told you, the vector of the allocation of the task. So for each task, for instance, Ti, alpha I will tell you where this task will be executed. That's why we can say that task Ti will be executed on data center M sub alpha I. Okay. Now we are interested to what I call data set to task assignment. I also said all about it because for each task, we need to know what are the data set that this task will be used. So we use a matrix F sub ij, which equal 1 if data set I will be used by task J and 0 otherwise. So this is what matrix is used to connect the data set to the task in our model. About the constraint, we mainly have one constraint, which is the storage capacity. So the sum of the volume of the data set that are assigned to a given data center should not exceed the capacity of that data center. This is a classical constraint that we have on placement algorithm. Okay. And finally, our data placement solution. This is what our algorithm will construct, is a vector psi, which provide for each data set where it should be located. So data set I called DI will be stored in data center MCI, okay, FEI. And then, as I say, in the second step of our algorithm is the replication. So again, we will use a matrix E sub ij, which is called 1 if data center I has a replica, has a copy on data center MJ, 0 otherwise. This matrix is something that will be dynamic because, as I told you, when you receive a data set, you use it for the task that asks for it, and then you decide to keep it or to delete it. If you keep it, then you update the matrix E by putting 1 to indicate that you has a copy of the data set, or 0 otherwise. Okay. This is the mathematical model of the overall data transfer time. So it looks complicated, but the idea is rather simple. For each task, That's why you have here a sum over the task. The first sum is over the task. So for each task, we consider all the data transfer that are related to that task. So that's why you have the second sum here, the sum over I. So it covers all the data set. Here, the coefficient Fij is just there to tell you if task I really need data center, no, if task J really need that data set I. And the second term here is just the cost of transferring the data center this I from its source Si to where the task J is executed, alpha J. And this cost is given here below, formula 7. So the first part of the formula 7 on top of the brackets is just 3 terms. The first one is the cost of reading the data set from the source, because there is a reading speed. The second term is the cost of writing it at the destination. There is a writing speed, the vector W. And the third term is the cost of the network transfer. So we have 3 terms. And those terms are summed up here to form the cost of transferring the data from the source to the destination for the given task. And then we do it for all the data set that the task requires. And let's give you that formula. And this is for one task. And if you do the sum for all the tasks as it's done here at the first step of that formula, we get the overall cost, the cost of the total cost of the overall communication in the geo-distributed cloud here. And this is the cost that we want to minimize, okay? This is the classical mathematical programming formulation for those who plan to use mathematical programming framework to try to solve the problem, okay? But from my experience, it's very difficult to solve the problem like this directly using a mathematical programming framework, because here you have this chronicle symbol here. This chronicle symbol is something that is not continuous. So it's difficult to model. If you really want to use, this is my opinion, a mathematical programming framework for this, then you have to replace this chronicle symbol by a large binary matrix, which is the same. I mean, it's a corresponding, but that will just replace something which is not contiguous, but something which is more regular. But in our case, we are going to solve the problem by a heuristic, because the problem, as it is formulated, does not allow a solution using directly a mathematical programming framework. And trying to look for the optimal value, for me, it's optimistic, because even what we are doing here is just a model. So the reality is not exactly the same. So I don't think it's really necessary to look for the optimal itself. So an heuristic will be just sufficient for me. So this is the first step of our algorithm. In the first step of our algorithm, we just compute the matrix of the transfer time. As I told you, for each data set, we want to know the cost of transferring that data set from a given data center. I repeat, data set I, we will say, what will be the cost if it were stored on data center 1? What will be the cost if it was stored in data center 2? So this gives you a matrix, tau ij. So tau ij will give you the cost of transferring the data center dataset I if it is stored on data center J. Then we will use it to try to look for the best location, okay? So here we have just run, you considering the task. So this third loop is over the task. So task TK here run on data center alpha J. So what we check, just check here if with the coefficient Fik, if dataset task K really need data center I. In that case, Fik equal 1, and then we just accumulate the corresponding transfer into ij. So we iteratively, like this, compute the matrix of all alternatives of data transfers, okay? And then at the end, we just sort row by row. So for each row, we just sort it. It's not mandatory to sort the row. We just sort it because we want to access to the optimal value very quickly. Because if you sort the row, the optimal value is at the first place. Okay? Later on, we will see that sometimes if you just choose the optimal value, the algorithm won't work. In that case, you move to the second best, and so on, and so on, and so on. Okay? So this is important to understand here. For each data set, I try to check for the best location, and then I got the matrix. This is the matrix 2 here. So one could say, okay, from this algorithm, since for each data set, you already have the best location, then the problem is solved. You just store it there. That's true, but there is an issue. Remember that we have a capacity constraint. So if you just consider that you already have from this algorithm the best location for each data set, and then you just assign it that way, maybe a given data center will be the best location for several data sets. And when you will sum up the volume of those data sets, it will exceed the capacity of the data center that has been chosen. That's why we are going to run a more sophisticated algorithm to avoid this situation. I'm just going to give a rough idea of this algorithm. So the previous one has computed for each data set the best location. Now we are going to refine that initial solution, taking into account the constraint, capacity constraint. So that's why here we have this iteration. So we try to revisit all the data set. And if we can, the data set is not already placed, we consider the best location provided by the previous algorithm. And then we check if the capacity constraint is not violated. This is line 15. Okay? And if it is that case, then we place the data set at that location. Otherwise, we consider that this is not a good solution. So we avoid choosing that value. So the algorithm here is iterative. Okay? Here, if the location exceeds the capacity, then we will just have to reconsider the placement that was provided by the previous algorithm. So that's why we record here, the end is where we got an issue, because we will have to correct the initial guess that we have, okay? The algorithm here, as I told you, when you sort the value of the best location, the first one is the best, the second one is the second best, and so on and so on. Here, the counter C just indicate the level of the choice that you are going to perform. So if everything goes well, then you are going to take the best one, which is the first choice. In that case, C equals to 1. But if you didn't succeed, then C will move to C plus 1, so 2. You are going to consider the second best, and so on, and so on, and so on. This is the idea of the algorithm. If you are not lucky, maybe iterating like this, you will go out of the possibilities. So the coefficient C will exceed the number of the possibility, which is the number of the column of the matrix so that we computed by the previous algorithm. In that case, the algorithm will not provide a placement for some data set. For me, we can correct this by just considering default choice, by always checking that we are not exceeding the capacity of the data center. So this leads to the solution of our problem, which means for each data set, where to place it, on which data center to place it. Now I talk about the replication. I said that the placement that we got here is a static placement. So for each data set, we know where it is. But the problem is when your task is running, the data set are moving from one data center to another. Maybe you should not delete a data center that you have received after using it, because a data center that are a bit more close to you will require it. In that case, it will be better to get from you rather than from the original location. That's why here we are going to consider this possibility, the replication. This replication already exists in the standard management of the cloud system for security, no, for robustness reason, for failure reason. But in general, this is seamless to the user. The user don't have access to this replication. Here we are considering an explicit replication. So we know that there is a copy of a data set on another data center. And when we need a given data set, we are going to consider the best source to get it instead of the unique source that was provided by the first algorithm. So I'm going just to give the idea of how this second part works. So as I said, when we use dataset transfer to create a replica, by deciding whether or not we decided to keep a dataset that we have received or not. So when we keep it, it's a replica. So when a data center require a data set because of the tasks that are running on it, then we have to choose the best location. So the way we solve it here, we use an array of the best location. So if you remember that the output of our algorithm is for each data center where it should be stored. Now it is for each data center where is the best place to get it. So this is another vector. And this vector is updated each time there is a new replica. Because when there is a new replica, there is a new location of data set. So maybe the replica that has just been created is the best location. So this is kind of distributed process to update the vector of the best location. When there is not enough space, and this is another problem, to store a copy. So you receive a data set, even if it's good for you to keep it because your neighbor will need it, but maybe you don't have enough space to keep that replica. In that case, what we choose to do here was to try to see which data set to delete in order to be able to store this replica, which looks interesting. So we have developed another algorithm to look for the data set that we can delete in order to get the new copy, which looks interesting. So there is also another strategy to look for the data set to be deleted, okay? So now let's present the experiment. We did some experiments of this algorithm using a simulator, Cloud Sim, which is a standard simulator that is used when we are doing investigation on the cloud. So this is the scenario that we have considered. So we have considered 5, 10, 25, and so on as a number of data sets. And size of each data set was between 1 terabyte to 100 terabytes, we have used a various number of data centers too, 5, 10, 15, and so on. And for the data center, the capacity, the storage capacity also is a value that varies between 1 petabyte to 25 petabyte. And we have considered a storage cost of $0.1 per gigabyte and a transfer cost of $0.05 per gigabyte. So the first result that we are going to present here, in this first group of experimental result, we fixed the number of data centers and increased the number of data sets. Okay. In the first figure, for instance, in red, we have the solution when we use only our static data placement. In green, we have the solution when we are using our static data placement enhanced with our dynamic replication strategy. In blue, we are comparing with a solution provided in the literature by Claude. So what you can see is roughly the curve in green, which is our solution, overall solution, static and dynamic replication, is the best. Only using our static placement is, let's say, the solution for Claude is improve our initial solution, but we are doing better considering the static placement and the replication. Okay. We also have the same situation when we are moving to 10 data center. So we always the best. In all our experiments, 15 data center, 20 data center, 25 data center. So moving the data set from 5 to 200, we always debate, always. So what we can say here is that our first static placement is not so bad, because I would have said that it's close to the Claude solution, even if the Claude solution is best, is good compared to our just static placement. But static placement plus replication strategy clearly provide a better solution compared to at least that example from the literature, and for sure from the pure static placement strategies. The second round of experiment, we fix the number of data set and we move the number of data center from 5 to 25. So the case of 5 data set, 10 data set, and so on. What we can see is when we fix the number of data set and move the number of data center, sometimes with the first static placement, the execution time increase. This is not surprising because when you increase the number of data center, what is changing is the topology of the interconnection between the data center. So you are not increasing the total volume of the data that are being exchanged over the network. You are just increasing the number of nodes in your graph. Okay? So our static placement algorithm seems, let's say, to incur a transfer cost that is increasing when you increase the number of data centers. But surprisingly, using the solution from Claude and our solution, static plus dynamic replication, the execution times is going down when you increase the number of data centers. The intuition, from my point of view, is that when you increase, as I said, only the number of data centers, you are not increasing the volume of data that are being exchanged within the network first, which is a good point because this is what is costly normally. But since you are increasing the number of data centers, for me, you are just providing more possibility to choose the best source for sending or for getting a data set that is required by a given task. So the more you have the data center, the more you have the possibility to perform a better choice. That's why the overall execution times goes down, because the cost, the overhead of exchanging the data is going down too, okay? And you can see it from our solution in green, which even in this case also outperform the solution that we consider the literature from Kubili. But it's interesting to see that it's decreased, okay? We also see it here when we goes to 55, 100, and 200 data sets. So this is what we could do for this work. Compare ourselves to one example from the literature, consider a static replication strategy, and then improve it with a dynamical correction by replication. From the perspective, I think that we might be interested in investigating a more final way to use the replica, because what we did here was to always consider the best source for a given data set. But normally, for a given data set and for a given data center, the best source should not always be the same. So we might consider a matrix, not a vector, of the best source between data set and data center. So even for one data center, there might be different good sources depending on the data center. So this is something that we might consider for future work. Another aspect, which is purely technical, is the way that we measure the data transfer time. Here in this work, we measure it using formulas and using the output from CloudSim. But there are also third-party tools that can be connected to CloudSim to get those information in a more final way. We didn't use it here, but this is something that we should consider if we remain using simulations. This is a classical when you are doing a work in a cloud. If you start with simulation, this is always the case, then you might consider moving into the real cloud. So this was not done here because, well, the work is at the beginning. And the second reason is, since we are saying that we want to minimize the cost of the data transfer between the network, which must be costly, not only in time, but also in monetary, then we have to be prepared for that, okay? So this is something that we will consider in perspective, but before doing that, we will evaluate what will be the cost for us. So thank you for your attention, and if you have questions, remarks, I'm happy to answer.
Thank you, Claude. It was an interesting talk, and we have here one question from the audience. I'll put here on to you. It was from Professor Leandro Santiago, and he asked something I was curious about too. What's happened in the case of a data center mapped to the array of the best locations is out? Do you have any fault tolerance technique, or you just recalculate the best location? What happens?
We didn't consider this case, but I think that the replication strategy will also address this problem. Because in case of fault, in case of failure in a given data center, if you have a copy, then you have to consider that copy. I said that the matrix of the best source was a vector. The vector of the best source was something that is updated dynamically. In our work, we were updating that vector only considering the cost of the transfer. But with your remark, I can say that we can also consider to update that vector considering this kind of failure.
Okay, I see. Thank you. Actually, I'm asking one question for myself now. You said about the replica choice and how every time a data set is transferred to another data center, you choose to store a replica or not. My
Okay.
question is, when they decided to store a replica, they take into account the space it has, or because you said about the when there is no storage available, and if they don't take into account, it can be the case that when they look for one data set to delete, there is no one available for, there is no one good to delete, and they cancel to stay with the replica. I don't know if I was clear, sorry.
Yes, I understand. Yes. If we discover that there is no good data center to delete, then we cancel the replica. So the replica is not, yeah, we can just cancel it. We don't replicate, we don't keep because in the worst case, you can decide not to replicate at all. Okay, so the point we were, if your first data set to data center assignment was correct, it should work. So the replication is just something that you are trying to do in order to improve the static assignment. But if it's not possible, because for instance, as you said, if you see that you don't have enough space, but you consider that it's interesting because you have estimated that your neighbor are going to ask that data, then you want to keep it. Then you are going to look for someone to delete in order to be able to store that copy. But if you see that there is no one which can be deleted, then you just consider to discard your intention to create that copy. Yes, clearly.
Okay, thank you. The next question is from Alan. It's from a student here in WUF. And it's kind of similar to mine, related to mine, because he asked about if the logic used to delete a data set is the least recently used, or there would be other, or it depends on the future assignments. I don't know.
I didn't understand. Your question is the question that I'm reading here about Lucia, or
no? There is one before from Alan Nunes. When the data center has no storage left, is the least recently used logic useful to free storage?
It's possible. It's possible. You can decide to use such a policy. But in our case, we didn't consider the least recently used logic. We were just considering the transfer cost. Only that. So if you revisit, and another thing that I didn't mention clearly, what we are going to delete is not an original value, because at the beginning you store the data set within the data center. Then when you are running your application, you create copies, replicas. On a given data center, when you want to create a copy, as I said, you are going to look for some data set to delete. But the data set that you are going to try to delete are only replicas, not the original one. But the only way to delete the original one is if you have the information that it has been used by all the tasks that requires it. Then you can delete without any consideration because it's already used. So there's a lot of way to decide to delete the data set. One of them could be least recently used. It's exactly like in the cache memory, exactly the same problem like in the cache memory. So here I think that for the cache, it's very difficult because it's hardware. So the cache has no way to see if a data is going to be used for the rest of the program or not. But in a cloud, since we have the scheduling, we can check at a given time if a data set has been already used by all the data, the task that could ask for it. Then we just delete. But the question is, yes, using the least recently used could be another possibility, but avoid to delete the data set that has not been used if there is no copy also.
Okay, thank you, Claude. There is one last question from Professor Lucia Drummond. In some commercial clouds, a storage service is offered where the user does not have control about the physical location of the files, S3, for example, in Amazon. In this case, I think that your solution might be adopted by the provider and not by the user, right?
Right, she's right. This is what I said, that the indication of our work is something that you have to give to the provider to take into account, because the user always work at the level of the virtualization. So you don't have access of what is going on behind you. So this is something that you have to give to the provider to take it into account, unless the provider gives you access to that part, which is unlikely. So she's right. It's something that has to be managed at the level of the provider. But you give him the indication from an algorithm like ours or other strategies.
Okay, I see. One last question for me. So your problem is an offline scheduling problem,
Yes.
like you know
The
all
first
the
one.
tasks, and there is no way there. And you think it would be easy to consider online tasks, or it could have, I don't know if I think it would be easy, but I think I don't know if it would be hard to compute everything and all the connections.
For me, I think it will be hard. The main issue here is always this problem between virtualization and the reality. You don't have the information, but at least for the initial placement, we assume that we are working at the level of the provider. Then he has the information that can do. And then the second step, this is offline. And then the second step, which is managing the replication, this should be clearly online. But again, we have to do it at the level of the provider because we need to have clear information about the real topology and about where the data are, because at the virtualization, at the virtual level, we don't know exactly where your data are. So you are going to make wrong assumption. So yes, it's possible and advisable to do the second part online and the first one offline, but both at the level of the provider.
Yes, I see. Both of the level of the provider. I don't know if you have any more questions. I think we do not have anyone. So thank you very much for your talk, Claude.
Thank you very much.
Thank you for presenting this work for us. And
okay.
now I'll switch to Portuguese to give some to talk to the audience.
Clearly.
Muito
obrigado.
Então, pessoal, obrigada, Claude. A gente acaba aqui essa primeira palestra. Daqui a pouquinho, às 2h30, a gente tem a nossa sessão com os trabalhos dos alunos. Lembrando que a gente já mandou por e-mail os links do Meet para quem está inscrito, e a gente pede para quem puder entrar com o e-mail que se inscreveu, a gente agradece. Então, muito obrigada a todos e até mais tarde.